Hey folks, Mrs. White here, coming at ya from my living room like normal during nap time, ready to teach you a little bit about inverse functions. So today we are starting with section 5.3, and we're going to be talking about inverse functions today. We're going to be talking about what the heck is an inverse, how is it applied to coordinate pairs, how can we apply it to functions, and then how can I graph both of those things, both the inverse and the original function. After we talk about that, we're going to talk about, or you're going to not talk about, you're going to do a little Khan Academy practice about finding inverses of linear functions. We are going to have to find inverses of nonlinear functions also, but this is a nice way that you can practice the simplest of the equations that you're going to see. Next, you're going to look at, or we're going to talk about how do we verify if two things are inverses, and we're using compositions to do that. And that is why it was really important, folks, that yesterday we did that review that involved compositions in it, because today we're going to be using that as we determine if things are or are not inverses. So hopefully you're feeling okay-ish about that. If not, like always, you're more than welcome to come see me during office hours. We can review compositions. We can review this stuff. We can review other stuff, whatever you want to do during those office hours. It's up to you. Okay? You do have kind of two homework assignments tonight. One of them is I am going to check Khan Academy. I do want to see that you got a 75 or better on this specific skill that I sent you. And there's a worksheet attached to the Google Classroom assignment, and there's only 3 problems there, and they're determining if something is or is not an inverse. So Khan Academy is practicing these skills. The 3 problems on that worksheet are practicing these skills. Okay? So we're going to start off today just by reviewing how to do a composition, but I don't know if we've really done anything that has a third degree yet, or a cubic. Okay, so we're going to do compositions today that involve both this third degree and a linear equation. Okay, so let's start off by reviewing and looking at f of g of x. And now, sit and begin, folks. You're welcome to pause the video and solve it yourself. It's just kind of supposed to help you transition back into getting into the math stuff that we're doing. So in f of g of x, I'm going to start by taking my g of x and plugging it into my f function. So I'm going to take this and plug it in for this x right here. So it's going to go this right there. So I'm going to have a 4. But instead of an x, I'm going to replace it with this little binomial in parentheses. So x to the third plus 2. And then up here in my f function, I've done my x. I still need to include the minus 1. Now I need to simplify that. So the only simplifying I see is I have a 4 on the outside of parentheses. I'm going to distribute that. And then I know I'm going to probably have to combine like terms after the fact. So I'm going to have a 4x to the third plus 4 times 2 is 8, and then a minus 1, and then the only simplifying I can do there is to combine like terms with those constants. So I have 4x to the third, and then I'm going to have a plus 7. Oops, that's a 7. Just go with it. Okay? So that is this composition of this function. Now here's where it can get a little bit trickier, okay? In fact, this is going to be a long problem. Okay, a long problem. I'm going to look at doing g of f of x. Now the reason this is going to be a long problem is because I'm going to be taking this chunk and I'm going to be plugging it in right here. But when I take this chunk and plug it in there, this whole thing is going to be raised to the third power. And you may or may not remember this right now, but if anything that is a polynomial is raised to any exponent, you have to like double distribute, like, oh my goodness, okay? So you'll see what I mean in a second once we write it in. So instead of putting in x to the third, I'm going to put in 4x minus 1, right? I'm taking my f of x function and I'm plugging it into my g. And then I'm going to have a plus 2. Now, this isn't bad, but this is not great. What this is telling me to do is take 4x minus 1 and times it by itself 3 times, okay? 4x minus 1, 4x minus 1, 4x minus 1. And right now you might be like, can't I just send that 3 across here and here? And the answer is no, you can't. You can only do that if you are dealing with a monomial in here, not a poly. So to go about solving this, oops, and we should have a little plus 2 here, right, from that, okay? I'm going to send this 4 here and here. I'm going to multiply the first 2 together first, okay? So I'm going to have 4x times 4x, which is 16x x squared. Then I'm going to have a 4x times negative 1, which is negative 4x. Then I'm going to take this and distribute it here and here. So negative 1 times 4x is negative 4x. And then negative 1 times negative 1 is positive 1. And that's just the product of these two. So I'm going to simplify that really quick. I get 16x squared minus negative 4 and negative 4 is negative 8x. And then a plus 1. I'm still not done. I have to times that by this chunk one more time. And then I have to make sure that I add this too, okay? That still isn't gone away yet. That was in my original function. All right? So I think I'm going to need some more room. I'm going to take, and you could do this either way you want. You could take this piece and send it here and here, and then the negative 8 here and here, and then the 1 and here and here. I'm going to work backwards. I'm just going to send this 4x to all three pieces first. So 4 times 16 is 64, and then x times x squared is going to be x to the third. I add those powers. 4 times negative 8 is negative 32x times x is x squared, and then 4x times 1 is going to be a plus 4x. Now I'm going to take that 1, okay, and I'm going to do the same. I'm going to send it here and here and here, okay? And that's really just going to change my signs. I'm going to have a negative 16x squared. I'm going to have a positive 8x. And I'm going to have a negative 1, and I'm going to bring down this plus 2. Whew. Now I'm finally going to be done, okay? I need to combine like terms here. Remembering when I combine like terms, I do not change my powers. So my highest power is x to the third. There's only one of those. Done. Next, I have negative 32x squared and negative 16x squared. So negative and negative, same sign, add and keep. Negative 48x squared. And then x to the first power, I have 4 and I have 8, so that's a positive 12x. And then negative 1 plus 2 is just a plus 1, okay? Wow, that was a lot of work to do this composition, okay? And again, that goes with my g of f of x, okay? I should put that label right on in front, just like I should have put it here. So when we're dealing with a cubic, remember, it means you are taking this and you are timesing it by itself 3 times, okay? Boom, boom, boom. Because this is not a monomial, I have to do that double distribution or foiling, depending on what your math teacher said. I'm going to say double distribution from this point forward, or triple distribution, or whatever. You just got to distribute like crazy. So let's move into talking about some new stuff. Let's talk inverses right now. Okay. So again, this is section 5.3 in your book. If you want to take a look there at the definitions, I like to include definitions from the book and what we're talking about because it helps you see some math language and some math notation. So inverse relations, two relations, and I want to remind you folks that a relation is a set of ordered pairs, okay? So two relations are inverse relations if and only if one relation contains the element AB, then the other relation contains the element BA, okay? If that's true, then A and B are inverse relations. So let's take a look. This and this, isn't it magical? They take the X and the Y and they flip them. Here, we take the X and the Y and we flip them. Here, we take the X and the Y and we flip them. So guess what we have to do? To have an inverse relation, you take your X and your Y from your coordinate pairs and you flip them. Okay, it literally is that easy, and that's specifically an inverse relation, okay? That's not an inverse function, it's an inverse relation. So let's do one, and we're going to graph it up, okay? And then we're going to kind of come to a conclusion about how inverses are related to the original. So the vertices of triangle ABC can be represented in this relation, okay? 1, 2, 3 coordinate pairs. So let's just plot this really quick. I'm going to go over 1, down 2. I'm going to go over 2, up 5. Then I'm going to go over 4, down 1. Okay, so you can see my original triangle is right here. Okay, now we need to find the inverse of that. So we'll do that in a different color. Let's go pink. Okay, so if we look at our information above, we're still going to have 3 coordinate pairs, right? They're in curly brackets because that's how we represent a set of ordered pairs, which is a relation. All we have to do is flip-flop our x and y. So instead of 1, negative 2, it's going to be negative 2, comma 1. Instead of 2, 5, it's going to be 5, 2. And instead of 4, -1, it's going to be -1, 4. And I'm going to plot these up right now. So I'm going to go -2, 1. So this point is the inverse to this point. Okay, so look at that in relation to this axis. Look at that in relation to that axis. So we see some similarity right there. Okay, our next point is over 5 up 2. Right there. And that was related to this point. Okay, if you remember, it was 2, 5, 2, 5, and now we're doing 5, 2. Our last point is -1, 4 right there. Okay, and hopefully you're like, oh, okay, I see this, and I'm seeing that it's 2 triangles, and I'm seeing that they're somewhat, you know, like the same size or the same area. Okay, the big takeaway here, okay, besides the fact that you graphed an inverse, yay, good job, okay, is that an inverse is a relation or a function or whatever it is reflected over the line x equals y or y equals x. So the line that has a slope of 1 over 1 and begins at 0. Every inverse always is a reflection over this line. Okay, so when I'm saying, oh, look at that, 1 from there, 1 from there, 1 from there, 1 from there, and then these are actually like 1.5 boxes away from the dotted line. I mean, it should always have some sort of relationship like that, because an inverse, if done correctly, is always a reflection over the line y equals x or x equals y. Okay, and we're going to see that when we start looking at functions. Relations are nice and quick and easy. You just flip-flop your x and your y. Okay? Now, as we start thinking about inverse functions, good news is flip-flopping your x and your y is still kind of a thing. Okay? So let's take a look first at what the book says as far as the property of inverses as we start thinking about functions. So, if f and f kind of to the -1 power. Okay, now it's not really -1 power. This is a notation for it being an inverse. Okay, if f and the inverse of f are inverses, then f of a equals b. If and only if the inverse is f of b equals a, right? Kind of you take that output, you plug it into the input, you take that output, you plug it into the input, okay? They're vice versa, all right? So let's do an example of that right here, okay? And I know that's tricky. Math definitions usually are pretty tricky. And then once you see an example, it makes some more sense. So let's see this and represent its inverse like this. Okay, so what they're saying is, if I pick a number and plug it in here, okay, so let's just pick a number. Let's pick like something nice, like, I don't know, let's do 6, okay? So let's say I solve f of 6. So 6 is going to become like my a value, okay? And we'll figure out what b is by kind of doing some math. So instead of x minus 4, I have, because I'm plugging in the 6 minus 4, and 6 minus 4 is 2. So this is kind of like my a, and this is kind of like my b, right? From this situation. So now I'm going to take what they're assuming is the inverse, and instead of plugging in 6 for an a, it's telling me plug in my b, plug in this piece, and I should get out this, right? The x and the y should be flip-flopped, the input and the output. So let's plug in 2. If these are inverses, okay, if this and this are inverses, then I should get out the input here, right? 6. So let's see. I'm going to take 2. I'm going to plug it in here. 2 plus 4 is 6. Oh my gosh. So it is the B and it is the A. So because this holds true, they are inverses. Okay? And that's just kind of a property of inverses. You know, your input and your output has to be your input and your output. Okay? It's kind of flip-flopped. Now, writing an inverse seems like it's going to be hard. It can be tricky, but the general process is the same always, every time. Okay, so the steps that you're going to do, the first thing you're going to do is you're going to replace your x with your y and your y with the x. Or you could say kind of flip your x with your y and your y with your x. So what that means, if we're looking at this function, okay, f of x is like your y. Okay, so my first step is to change their locations. Instead of y equals 2x minus 5, I'm going to do x equals 2y minus 5. Okay, I'm going to flip-flop my x and my y, just like we did with coordinate pairs, kind of. Once I have that, and this is easy because it's a line, folks, okay? Once I've change the locations of my x and my y. I'm going to get my y alone and positive. Okay. And that's going to make it so that I'm able to graph it. And I'm going to do that if it's a line. I'm going to do that if it's a quadratic, which means that our x would be squared. I'm going to do that if it's a cubic or a fifth root or whatever, okay? So we're going to see things that have powers higher than 1 and 2 in this chapter, okay? So let's make that happen right now. Let's get our y alone and positive. So 2y minus 5, my first step has to be to add 5 to each side. I'm left with x plus 5 equals 2y. Divide by 2. Now my y is alone and positive. I have y equals. And then because I want to graph this, I'm not going to leave it like x plus 5 over 2. I'm going to send this denominator here and here. So I'm going to have 1/2 x and then plus 5 halves. And because this is an inverse, I'm going to relabel it now. I'm going to take my y out. I'm going to label it with my inverse. Function notation. Okay, so the inverse of f of x is 1/2 x plus 5 halves. And I'm going to give this a go for graphing. It's not great. Okay, it's going to start at 5 over 2, which is going to be 2.5 or 2.5. So I'm going to go up to 2.5. I am going to go up 1, forwards 2, up 1, forwards 2. I'm going to go down 1, backwards 2, down 1, backwards 2. And here is the inverse line. Okay? Now let's do our original one. We'll do that one in pink. It was y equals 2x minus 5. So this one's going to start down at minus 5. And it's going to go up 2, forwards 1, up 2, forwards 1, up 2, forwards 1, up 2, forwards 1, up 2, forwards 1. Okay? And it goes like this. Now, if we take a look, okay, and at first you're like, I don't know, those don't seem to be exact opposites. Well, they're not exact reflections. It's not a reflection over the y. It's a reflection over the line y equals x. So once you kind of take a look at that, you're like, oh, I can see how that works for sure, okay? It's going to definitely be a reflection over these. You can see that they both look equidistant from that green line, okay? Let's try a couple more of those, and then I want you to practice it on Khan Academy. Okay, so let's do one that has a square in it this time. So maybe we graph this one up first. Depending on who you had for math, you know how to kind of tackle this right up from the get-go. I know a lot about quadratics, and so we could create a little XY chart, but I know this is going to be my standard graph for x squared shifted up 1. So it's going to have a vertex here, and it's going to go something like this. Okay? So that's my original function. Now I'm going to write my y in here, and I'm going to do my 2 steps, which is to change the y and x, and then just get my y alone and positive now that it's in a different spot. So I'm going to have x equals y squared plus 1. Okay? To get my y alone and positive, I first always get rid of my add subtract. I'm going to minus 1 from each side. Now here's the dilemma, and we have to think back to our quadratic unit, right? This is a y squared. We have a property for that. It's called the square root property is how we get rid of it. Whatever power you have here, folks, you get rid of it by doing the root that corresponds to it. So to get rid of a y squared, to get rid of that squared, I'm going to square root it. And hopefully that's familiar from when we did completing the square. Okay? And I'm going to square root one side. I got to do the other. Now my y is alone and positive. I have y equals the square root of x minus 1. Okay, y equals the square root of x minus 1. Now, you might not know how to graph this. I don't think you probably do, because we're going to be learning it literally in our next lesson. But for now, what we could do to graph it is make a little table. Make a little XY chart. So, I'm going to pick some values of x. Let's say we try 0, right? That's a nice one. Let's try 1. Maybe 2, and maybe 3. Okay, so I'm going to plug in 0 here. 0 minus 1 is negative 1. The square root of negative 1 is imaginary, right? The square root of negative 1 is I. It's imaginary. Can we graph imaginary on here? No. So what that means, folks, is this graph does not exist at 0. Okay? Because you end up with a negative under there. It would be an extraneous solution, which again, we'll learn about a little bit more later, to have a 0 in there. Now I'm going to plug 1 in. 1 minus 1 is 0. The square root of 0, so what times itself is 0? It's 0. So my first point is going to be over 1 up 0. Look at that. Boom, reflected right there. Nifty. Let's plug in 2 now. Okay. So 2 minus 1 is 1, and the square root of 1, so what times itself is 1? It's 1. So I'm going to go over 2, up 1. Then I'm going to plug in a 3 right here. Okay. 3 minus 1 is 2, and the square root of 2 is not a nice number. That's an irrational number, okay, which means it's a hot mess decimal, but I can do it on a calculator, and I'm just going to approximate it. So I'm going to go turn my phone calculator sideways. I'm going to type 2. I'm going to press the square root button, and I get 1.412, blah, blah, blah. I'm going to keep it as 1.4 right now, okay? So I'm going to go over to 3 and up 1.4. So a little bit less than that half. So this is going to be our square root curve. It actually ends up kind of leveling off a little bit. It does still increase, but at a slower and slower rate. Again, if we take a look at this graph, right, and I draw my line starting at 0, 0 with a slope of 1 over 1, boom, it is a perfect reflection. Now you might be saying, Miss White, how come we don't have a bottom part here? Well, I can answer your question with another question. If I had a bottom part here, is this now a function, this black line? And you might not remember how to answer that. A function has to pass the vertical line test. It can only hit that vertical line once, okay? Because in this situation, we would hit it twice. We only end up graphing our top part, okay? And then it doesn't go behind this because those would be imaginary solutions, okay? So by only graphing what we call our principal root, the positive version, because we do, when we used to simplify square roots, we would always put plus or minus in front, right? Well, when we're graphing, we're doing our principal root here, okay? So our square root is going to give us just our positive value, because if not, it's not going to be a function, and by definition, it's got to be a function, okay? All right, so these two below, what I'm going to do is I'm going to solve them quietly. After I'm done this first one, I will turn the volume back up and explain it to you, and then I'll do this one with the volume back down, and then I'll turn it up and explain it to you, okay? That way you can give them a go on your own. Alrighty, folks, so let's come together and take a look at this problem, okay? So, first things first, I wanted to find my inverse, okay? I could have graphed the pink line first. I held off on that because I knew it would be easier to just rearrange things this way. So I flip-flopped my x and my y. I said this whole thing's being divided by 5, right? So before I can add the 3, I need to times 5, and then add 3, add 3. So I started at 3 and went up 5, forwards 1, down 5, backwards 1. Then for my pink function, I distributed the denominator to both pieces, and I got 1/5 x minus 3/5. So I started here and went up 1, forwards 5, down 1, backwards 5. And you can see these two lines are a perfect reflection right over that line, y equals x. That lets me know I did it correct. Let's take a look at this next one. So folks, before I go too far, if you're not sure how to graph a quadratic, you can always do, you just need to get 3 points. So you can always make a table for that too. So if I put 0 in, and I always put 0, right? I test 0 because it's quick and easy. If I plug a 0 in for x, I have 0 squared, which is 0, 0 times 3, which is 0. So I'm going to have, this is my vertex. It's going to be at 0, 0. Next, I could plug in 1. 1 squared is 1 times 3 is 3. So I could go over 1 up 3. And then since this is my vertex, this would be, it has reflectional symmetry, right? It would be reflected over there. So here's my quadratic that represents that. Okay, I know sketching these can be tricky. I don't want you to stress out about sketching quadratics right now. We spent some time graphing those in the past. This is just to make sure you can understand the relationship between it and its inverse, okay? Actually, I'll just talk you through the rest of this problem since we already got started on it. So now, since that's my y, I'm going to flip-flop my x and my y. I'm going to have x equals 3y squared. Remember, the y is only squared. If it was 3y squared, there'd be parentheses around both. I'm going to divide 3, okay? And then I'm going to square root to get my y alone. So square root. And I'm left with the square root of essentially 1/3 x. And again, if you weren't sure how to do that, okay, we can make a table. Now, if x was a negative number, there's going to be a negative under the root sign, right? So I don't want to try any negative values here. I'm going to try 0. And then maybe I'll try 1 and 2. Okay, so when I plug in 0, 0 times 1/3 is 0, and the square root of 0 is 0. So boom, that one's also going to start right there. When I plug in 1, I get 1 times 1/3, which is a third. And then I have to square root it. So I'm going to come to my calculator. I'm going to clear everything out. I'm going to do 1 divided by 3, enter, and then my square root button. And it gives me this decimal, 0.57. I'm going to put my 2 here. 2 times 1/3 is 2/3. And then I'm going to square root it. So 2 divided by 3, enter, and then square root button. I get 0.816. Okay? So I'm going to graph these now. I'm going to go over 1, up about a half. I'm going to go over to 2, up to 0.8. And you can imagine this is very steep going right now. In fact, if I were to plug in 3 next, okay, 3 times 1/3 would be 1, and the square root of 1 is 1. Okay, this would be a nice one that I could have calculated without my calculator. That means at 3, I'm going to be exactly at 1. Look at that. I went over 1, up 3. Here I go over 3, up 1, the exact inverse of it, okay? And those two, this half and this, again, are a nice reflection, right over that line y equals x. So at this point, I want you to hop on Khan Academy. I've sent you all a skill, as long as you've joined the class, called Finding Inverses of Linear Functions. So we're going to be dealing with just lines here. No parabolas, no cubics, just lines. So I want you to give a go. I want you to try to do this a couple times if you need to make sure that you get a 75%. Okay, your goal is a 75%. Once you're there, move on. Do not worry about getting 100. Feel free to pause the video, go work on that, but please come back because we have one more thing to learn. And that last thing we're going to learn is how can we test if two functions are inverses of each other, okay? And this is directly tied to them being compositions of each other, okay? So, two functions, f and g, are inverse functions if and only if both of their compositions are the identity function. Now, you probably don't know what the identity function is, but the identity function is the line that the two inverses are reflected over. So it's essentially the line y equals x. So what will happen is when you do this composition and you get out your answer should look like just an x, okay? When you do both of the compositions. If you do not get exactly x, they are not inverses of each other. So say you get 2x, not an inverse. Say you get x plus 1, not an inverse. Say you get x over 2, not an inverse. Say you get x, it's an inverse, okay? And you'll see that we'll do these two examples together, and then we'll be done with our lesson for today, and we'll talk about your other part of your homework assignment. So the directions are: determine whether each pair of functions are inverses and explain your reasoning. You can explain with work. They're going to be inverses if I do the composition f of g of x, and I get out x, and then I do the other composition g of f of x, and get out x again. It has to work for both, okay? So let's do our f of g of x first. So f of g of x means I'm taking my g of x function and I'm plugging it into f. So I'm going to take this and I'm plugging it in right here. Okay, I'm taking that chunk and I'm plugging it in right there. So I'm going to have 3 times, not x anymore, I'm going to put in 1/3 x minus 3, and then my plus 9. And now I'm going to simplify this, okay? I notice that I have distributive property here. I'm going to take care of that first, okay? 1/3 times 3, hopefully you know that that's 3 over 3, which is 1. You could put it out over 1 if you wanted and do across the top and across the bottom. But either way, you're just going to get 1x, or just x. And then 3 times negative 3 is negative 9, and then on the outside we have a plus 9. Negative 9 and plus 9, oh my gosh, equals x. So this is my identity function, right? My y equals x. Perfect. That doesn't mean they're inverses, though. It has to work for both compositions, f of g of x and g of f of x. Okay? So now I'm going to take my f function and plug it into my g function. So I'm going to be taking this and plugging it in right there. Okay? So I'm going to start with my g function now. 1/3 instead of x, I'm going to plug in 3x plus 9. And then on the outside, I have a minus 3. And I notice again, to start me off, I have to do some distributive property. So 1/3 times 3, we just did it over here, right? That's going to be 1x. And 1/3 times 9, I put the 9 over 1. I go across the top and across the bottom. I end up with 9 over 3, which is the same thing as positive 3. I'm going to bring down my minus 3. Those cancel. Sweet! I'm left with x again. Because I got my identity function on both of these, yes, they are inverses. Okay, it has to happen on both. If you get a no on either of them, it is automatically a no. So let's do another one, okay? I'm going to start, it tells me again to test if they're inverses. I know they're inverses if I can take my compositions, f of g of x and g of f of x, and if they both equal 0, then I'm good. So g of x has to get plugged into f. So I'm going to take this and I'm plugging it in right here. Okay, and this does have a squared and a square root, so that could be a thing. Okay, so I still have a 4. Instead of x, I'm going to plug this in. 2 square root of x to the second power. There's nothing else here, so this is what I have to simplify. Now this is where PEMDAS is something you got to remember. So first things first, parentheses. Can I simplify anything in here? No. Next is not multiply the 4 in. Next is exponents, right? PEMDAS. So we need to do this exponent next. So this is a monomial, folks. There's no plus or minus, so I can actually distribute that squared to both pieces. This is the exact same thing as 4 times 2 squared, which is 4, and then the square root of x squared. Okay, and hopefully you're like, Miss White, square root squared, they cancel. I'm left with 4 times 4x. And 4 times 4x is 16x. Can I simplify that any further? No. Is this my identity function? It needs to just be x. No. These two are automatically not inverses. I don't even have to check the other one, okay? I only check the other one if it's a yes here, okay? If you get a no on one of them, you stop and you say they are not inverses because the composition, okay, does not equal x. It's not an inverse, okay? So that is what you need to do for your homework. So what I have for you attached is, these are 3 problems from your book. I think it's number 8, 9, and 10 from this section. I'm not exactly sure. It doesn't exactly matter. What you are going to do is determine if each pair of functions are inverses and show all your work. So I gave you 2 boxes underneath each of these because in one of them I want you to do f of g of x and show your work. Okay, and in the other one I want to see your work for g of f of x and show your work. Okay, now let's say I solve this one and I get a no here. Okay, it does not equal just straight up x. Do I have to do this one? That's your question, right? My answer is no. If this is a no, you do not even have to solve this one. You're trying to see if both work. If you get a no on either one of them, stop, write no, they are not inverses, and move to the next one, okay? I'm not going to make you solve it if it's not going to be necessary, okay? So remember, one composition here, the other one here, and your goal is, if they are inverses, you're going to do those compositions and get out just x, okay? Just x. I will tell you, I don't even remember what the answers are for this, but I will be happy to share those answers with you if you want to attend office hours tomorrow, okay? So if there's any confusion over this assignment at all, and or compositions of functions and how they relate to inverses, or how to graph inverses, any questions about this stuff or anything in chapter 5, please, please, please consider showing up to office hours, okay? It's not a huge commitment. You can stay, you can just listen, you can do your homework, we can do your homework together. It doesn't matter to me, but make sure you're utilizing that time if you have questions. Otherwise, folks, I'm all set. That is how we determine if things are inverses and how we create inverses. Thanks for your time today. I will see y'all later. Bye.